Many communities across the globe are still waiting for truly fast internet. Fiber to the home, often called FTTH, is the gold standard. It provides fast, reliable connections to homes and businesses. However, installing this infrastructure is filled with significant challenges. Building a fiber network is complex and expensive. The very first step, planning routes for fiber optic cables, is one of the hardest. It's a slow, methodical task that demands immense attention to detail and costs a lot in time and money. Planners face a puzzle of immense scale. They must chart the optimal path for every cable, poring over countless documents and data sources. Detailed geographical maps, lists of residential and commercial properties, complex local and national regulations. The goal is to connect every designated endpoint while navigating a hidden maze of obstacles. Underground water pipes, gas lines, existing electrical conduits, root systems of mature trees. Every decision must be weighed to avoid costly, dangerous mistakes. Planners must adhere to right-of-way laws and property boundaries to prevent disputes, delays, and reroutes. Artificial intelligence offers a powerful solution to these long-standing challenges. AI is not just about robots or futuristic concepts, it is about using computers to perform complex tasks that normally require human intelligence. In fiber network planning, AI acts as a skilled, tireless assistant, processing vast information far more quickly and thoroughly than any person could. AI systems can be trained to understand maps, satellite imagery, and regulatory documents, then explore millions of potential design possibilities in a fraction of the time. The core promise of AI is its ability to find optimized solutions, not just a workable route, but the best route for the goals set. It systematically minimizes digging and avoids underground utilities, protected environmental areas, and other obstacles, reducing accidents and delays. A well-trained AI respects the legal landscape by integrating property lines and right-of-way corridors, ensuring designs are compliant. Perhaps most importantly, it can design networks efficient today and built for low-cost expansion tomorrow, accelerating delivery while lowering CAPEX and improving resilience. For an AI to design a network, it must first see and understand the world, fed with rich, diverse data. Geographic information system maps form the foundation, sophisticated multi-layered maps detailing buildings, roads, sidewalks, and property lines, the canvas on which AI draws. High-resolution satellite and aerial images add real-world context, revealing trees, new construction, and temporary obstructions that GIS may miss. Existing utility maps show underground infrastructure. With this, AI knows what to avoid to prevent dangerous, costly strikes. AI organizes data into layers, each a simple fact, then overlays them to build a comprehensive model. Seeing all constraints and opportunities at once is hard for humans, but trivial when layered digitally, enabling efficient pathfinding to connect homes and businesses. Treating the area like a puzzle, AI constantly asks, is this path public land? Does this route cross a water pipe? By structuring data, it uncovers intelligent solutions humans might miss. Planners who use AI have several powerful methods: genetic algorithms, reinforcement learning, and graph-based neural networks. Genetic algorithms take inspiration from evolution, creating many initial plans, evaluating them against goals like minimizing cost and trenching, and evolving better solutions via selection, crossover, and mutation. Over many generations, the population converges towards superior topologies. A second technique is reinforcement learning. The agent builds a plan, gets rewards for good choices and penalties for bad ones, learning a policy that maximizes total reward. Finally, GNNs learn from past network designs. A fiber network is a graph, and GNNs, trained on archives, learn patterns that make topologies cost-effective across different neighborhood types. By recognizing what worked in similar contexts, the model suggests efficient layouts for new projects, accelerating planning and improving outcomes. The true power of an AI planning tool lies in balancing multiple, competing objectives with mathematical precision. The primary goal is to minimize trenching, labor-intensive, disruptive, and the largest budget item, finding the shortest feasible paths. Beyond shortness, AI is a vigilant risk manager, avoiding visible and buried obstacles, buffering utilities, and penalizing infringing routes to reduce outages, repairs, and accidents. Respecting property and row is non-negotiable. AI treats these as hard constraints, proposing no illegal crossings without recorded easements, saving hours of manual checks and shielding projects from legal challenges. A forward-thinking system may choose a slightly longer route now if it lowers the cost of adding customers later, prioritizing existing poles and ducts to cut costs and speed deployment. The result: smarter, safer, faster builds, lower CAPEX and resilient future-ready networks. Consider designing FTTH for a suburban town, 2,000 homes to connect. Traditional teams spend weeks gathering maps, property records and utility schematics, drawing and redrawing routes, producing a viable but compromise-laden plan with high trenching and costs. Now, introduce AI. Feed GIS maps, recent satellite imagery, property lines, and utility layers. Set objectives. Connect all homes, minimize trenching, use poles, avoid obstacles. The platform runs genetic and graph neural methods, analyzing millions of combinations, and within hours generates optimized options with reports on cost, trenching, and infrastructure use. One option cuts trenching by 20% via rights-of-way and clever shortcuts. Another reduces overall cost by 15% by maximizing aerial poles. The planner selects the best option. Approvals move faster, construction begins sooner, and savings are reallocated to other community needs. The promise is immense, but these tools aren't magic garbage in, garbage out. Performance depends on accurate, up-to-date inputs, ensure recent imagery, true utility locations, and digitized right-of-way rules. AI excels at optimization, humans catch on-the-ground details. Designs must be reviewed by planners and validated with site surveys before digging. Start small, form a dedicated pilot team, choose one neighborhood, set success goals like reduced planning time or construction cost. Use the problem promise-proof framework to communicate impact. AI will transform FTTH planning faster, cheaper, less risky. Leverage genetic algorithms, reinforcement learning, and graph neural networks with quality data and human oversight. Start a pilot, measure results, and iterate towards smarter builds.